operation. And we should start stage 3, not stage 3. And of course, we will start with challenges from your comment to report, please.
Okay, so we would like to challenge problem number 8 in order magnetic demonstration. We would like to challenge problem number 16.
We accept the challenge.
Alright, so now recorder have 5 minutes for the preparation.
Honorable judges and worthy opponent. This is Team Me1 reporting problem 16, cushion catapult. So the problem statement is basically about place an object on a large air cushion and drop several other objects in such a way that the first object is catapulted away. So we'll be focusing on the x velocity and other parameters by doing quantitative analysis. So for the phenomenon, when the ball collides with the cushion, you can see that the membrane of the cushion will present a wave-like motion, which the parameters of the cushion and velocity determines the relevant setting of the wave. And the collision generates two waves in different direction that creates a standing wave that its vibration catapults the ball upward. So for the introduction, there are the several parameters we'll be using in our further theory discussion. So we use the wave equation to solve the problem, and the general form is presented below. And the separation of variable method is applied in order to simplify the differential equation. And so we plug in the simplified function into equation 1, and we can get this equation 3. So after substitute those equations from equation 3, the result will be presented above, and this will be the result of the differential equation. So we can get the propagation speed through general solution of the linear wave equation that is affected by the tension of the cushion and the density of the cushion. So the collision causes two waves heading toward two directions. That the standing wave formed by superposition of two waves that have the same frequency, we can get to the equation 7. So solving this superposition process, we can get to, using this boundary condition, we can get to equation 9. So to solve this equation, we plug in this boundary condition into the former general solution of the differential equation. And we use a del function signifies the increase of density only on the position where the ball is located. And after solving those integration, we can get to equation 11. And plugging the boundary condition into the equation, we can get to equation 12. So substitute the equation, we can get equation 15. So analyzing the amplitude of the propagation wave, the maximum velocity of the ball will be as above. So as you can see in our solution, we can't really analyze it through the conditions we give before this ball falling to the cushion. Therefore, we would like to analyze specifically about those parameters, variables such as frequency, amplitude, and wave number. So next, analyzing the change of frequency through relevant parameters, we can get this elasticity, Young's modulus effect on this frequency by using this equation. So as you can see, this frequency can be affected by the size of the cushion and also the material that it used, including Young's modulus and the density. So we can get to this angular frequency though, in equation 20, and plugging back into the wave solution, we can get to equation 21. So the propagation speed of wave is also elastic membrane can be presented as equation 22. And next, I would like to analyze some parameters that can affect this amplitude of wave. So deriving the position before the static equilibrium between the ball and the cushion, we can generally analyze the factors that affect this amplitude. So as you can see, there's a simple calculation or simulation we use, and as a result, this amplitude should be related to the contact area, the mass of the bowling ball, the density of the pressure, and also the volume of the pressure. So for the experiment setup, we use a cushion and laminated PP woven polymer bag and dunnage and also different types of gases. And we use a baseball and also a semicircle styrofoam with weight inside. And also we added weight by using as above, and also use fiber to stabilize the falling ball's position. Because we also noticed that in our equation, this distance between the two falling balls can actually largely affect the result of x velocity. So by cutting the line, we can see that we can control the height or the velocity before the collision. So therefore, we can determine this, its relationship with the amplitude that we just mentioned. So here are the relevant parameters. First, it's the different mass of drop object, different gas pressure, different drop height, which affects the velocity, and also different gas and cushion, and different contact area, different size of cushions, and different texture of the cushions. So we augment the mass by adding weight to the project that is dropped. So a larger mass of the drop object will result in a greater x velocity, and as you can see in this equation and its relationship with those relevant parameters, it increased the amplitude and also the frequency. So as you can see in this graph, that the increase of weight too affects this x velocity of the second ball that is placed on the, originally placed on the cushion. And for experiment 2, we test different gas in the cushion. So as you can see in this graph, by using different gases, we didn't observe a significant difference between these gases. However, there is something we did observe, is that it has a positive correlation between the molecular mass and the time gap between the dropped ball touching the cushion and the emitted ball leaving the cushion. And this is because this molecular mass can actually increase this root mean square of the velocity in the cushion. Therefore, this fastened this process of catapulting the ball upward. So for the experiment 3, we used different size of cushion, and a larger surface area resulted in an increased loss of energy, and also the amplitude decreases and the cushion size decreases. And this is because if the contact area is bigger, which means there have more area created, that the pressure can actually act on this ball in order to stop it. So this amplitude will decrease. And as it's shown in those graphs, the tendency of the increase of area then fits our theory. So for the experiment 4, we analyze a different gas pressure. So if there's a sufficient amount of gas in the cushion, the amplitude will be restricted as the ball touches the ground. Conversely, when there's an excessive amount of gas in the cushion itself will restrict the amplitude. So this pressure is a main factor that will affect our amplitude. So if you look at those, just as what I stated, we can predict that there will be a certain highest point in this amount of gas, because the gas can perform different properties in different pressure. That if it's too high, it will cause the cushion unable to converse and create a large amplitude. So as you can see in this experiment, we do find a suitable pressure that can obtain the maximum x velocity, which it will be affecting the angular velocity, angular frequency, and the amplitude of the equation we derived. So for experiment 5, we analyze a different contact area, and as I just mentioned, the larger contact area between the drop object and the cushion leads to a reduced pressure and amplitude, and this causes the x velocity to decrease. So for the experiment 5, here's some results which fits the theory we proposed. So for experiment 6, we investigate the different texture of cushion. So in the theory part, we did discuss the Young's modulus and the density of the cushions effect to this frequency of wave that it creates. So this greater elasticity in the material will result in an increased amplitude and velocity. And this is basically based on this change of frequency. So as you can see in this graph that we changed 3 different bags with different material. It fits our analyzation through this density of the cushion and also the Young's modulus of the cushion. So for the experiment 7, we observed different drop height and effects to this x velocity that the ball is catapulted away. So dropping an object from a greater height leads to a higher velocity that creates a larger amplitude. So it's reasonable that we predict that as the height of the ball increase, the x velocity will actually increase. So for the conclusion part, the x velocity of the ball will be related to the Young's modulus of the cushion and the contact area of the ball, mass of the falling ball, pressure, volume, and the size of the cushion. And gas with different molar mass will affect the time gap between falling the ball and catching the second ball away. Thank you.
So the important questions.
Okay, so first I have some questions to you. First, how do you measure the exit velocity?
We measure the x velocity by using charcoal to analyze the displacement change throughout the time.
So in your theory, you mentioned like V equals square 2gh. Is that for the exit velocity or the ball that you drop?
If we're asking about the effects of air resistance, that part of calculation is actually just...
No. I mean, in your theory, you just mentioned V equals square.
Oh, that's the ball that's falling down.
Just falling down. Okay. Then you just mentioned about Young's modulus, right? So for the air inside the cushion or the cushion itself? Or
The cushion itself.
The cushion itself.
Yes.
Okay. Then, so in your conclusion, the exit velocity related to the pressure, right?
Yes.
Yes. Okay. Then is the things that just the cushion just the thing that just exit the cushion, is it vertical or there's some angles?
We exclude those kind of samples that includes the angle because it's easier to examine the whole distribution of vector through a vertical catapult.
Okay, so you said there may be some like angles, but it's
It depends on how the ball actually collides with the cushion in the first place.
okay. So you can't really control it, or you can.
Control the angle of falling the ball?
Yes.
Yes, we can control it.
Yes. Okay, then I think that is enough my short question.
The 3 minutes was important to prepare.
morning from TYPT, and my name is Chen Shi. So today I'm going to post problem number 16. So here's the problem statement, and we're mainly focused on the exit velocity and the relevant parameters. So here's the summary of report. So they are used linear wave equation, Young's module, and wave formula to trying to describe and explain how the ball is going up. And their conclusion is the exit velocity will be affected by cushion air amount, distance between two objects, and several other parameters like Young's module of the cushion, or the air pressure, or the tightness of the air. So here's some strengths and areas of improvement of reporter. First, they have good theory explanation, and they have simple and clear diagram with adequate explanation, which for us is very clear to read and understand what they're trying to tell us. And they have numerous parameters considered, which they have many experiments want to fit their theory. And they have mathematical theory used and single master formula used, and they fit their theory and experiment. But here's some areas of improvement. So first, they too focus on the theory and lack of experimentations in most of formula. So they just skip the formula and just like from 1 to 2 to 3 like this. And lack of quantitative result. And no direct relation between the parameters. So they discussed several parameters, but they didn't combine together and tell us which is the most important one. And they have no explanation on energy transfer efficiency. So here's some points of discussion that we'll want to discuss with the reporter in the later session. So first is the parameters, like amount of the air in cushions. How do they define it? From volume or from pressure or something? And the release height, the inner line, or we will have a maximum. And the boundary limit of the object that can be catapulted away, like the distance, like the Young's module, or like the pressure inside the cushion. And the angle of impact that I just asked in the short question that they didn't really explain clearly. And in the experiment, we want to ask about if the air was dissipated through the zipper and will affect overstretching. And how was the velocity measured? And the angle of the launch elastic of cushion, or like Young's modulus, and air resistance. And in the theory part, we want to ask about like energy transfer, which they just mentioned about the wave. So how does it transfer, and is there any decay of the energy? And the energy loss, and the energy transfer efficiency. So I think we can go into our discussion part.
So for discussion start, may I clarify about talking about the formula? So I didn't explain this side-by-side formula. Actually, those derivation is a technical, like solving the equation is a
Okay, so I understand. Then I have several questions that I want to ask you. So first is, in the QA part, you just mentioned that there might be some angle when it just exit.
Yes.
Right? So why does the angle would change? By what parameters?
So if the ball collides with the cushion in different angle, the wave will oppose in a different angle, therefore cause the catapult to actually catapult this ball in another angle. But in our experiment, we're focusing on perpendicular angle of colliding with the cushion,
Okay.
as you can see in our experiment setting.
Okay. Then, so in the problems, like in the videos, some of it, if I didn't remember it wrong, there's some rebounds of the ball. Like I remember that you just showed in the experiment that you change the pressure of the bat. So there's a rebound of the ball. So is that affect your experimental result?
Even the pressure,
No, the rebound of the ball. The bigger ball.
the bigger ball bounces the ball. So I would say
this is not the main focus of our theory, wave theory that we propose, but I do acknowledge that in the energy angle of examining this problem, it do have some effect. So.
Oh, okay. So you said you use like wave and to discuss about your whole experiment, right?
Yes.
So the wave should be just transferred outward. Just transfer outward. So how does the ball just respond? So is there any like wave just transfer back?
So when I discuss, maybe I didn't say it clearly as our problem. So when the ball collides with the cushion, the waves, if we consider it as a plane of one direction.
Okay, how about like you have very clear theory or can you use your theory to explain this phenomenon? The rebounds of the ball.
Rebounds of the ball.
The bigger ball will rebound. Like in the experiment that you change the pressure, can you just go to the page of the experiment? Next.
Okay, I understand your question. So actually, in our theory, you can see that this amplitude, our theory actually started when we can actually see the amplitude of the wave form. So it's actually not, our theory didn't include this ax of the first ball. So we can't really explain this ax velocity of the first ball that collides with the cushion. But
Okay. So then my next question is, you just mentioned that there's some the optimal distance to make the exit velocity the maximum, right?
yes.
Yes. So you use what theory, like standing wave or?
As you can see, this d in our equation stands for the distance between the two balls. So if we consider this problem in a wave perspective, it's reasonable that the ball will pumps in the most x velocity in this when the wave reaches the highest point in there.
So can I use that board? So if you use wave and you just mentioned you just mentioned standing wave, if I didn't get wrong in the theory part. So the standing wave has the peak and the bottom line, right? So do you observe this phenomenon like I have a cushion and my thing is put here, or here, and it has a big exit velocity, smaller exit velocity, and bigger exit velocity. Do you observe this phenomenon?
I understand why you think of that way. Good.
Yes.
So you're thinking in that way is because you believe that there's a fluctuation of waves.
Yes.
Exactly. But however, in our calculation, you can see the standing wave actually has a pretty long wavelength. So therefore,
You say pretty long. How long is it? The wavelength. You measure.
it depends on different condition of the bowling ball.
Okay. So how do you measure the wavelength? You say they have wavelength. How do you measure? You say it depends on the different parameters. So how do you measure in experiment?
It's not a necessary variables that we need to measure in order to get to our result. So
But you said so like there's a peak or is a one, and it just affects how the exit velocity forms. So I think it's necessary for you to measure the wavelength.
but we did include the distance parameters in our equation.
So okay. Then in the contact area, you change the size of the ball or you change the place that you probably.
For the contact area, we actually stick a square under the ball. Therefore, we can specifically control this contact area between the ball and the cushion.
So you're under the ball.
Yeah,
So when you drop the ball here, and you drop the ball here, it has different area. Am I understanding right?
we didn't conduct this kind of experiment in our.
No, so, okay, so can you
we define it referring to the area that this ball actually collides with the cushion. So the way we change it is to, for example, this a ball like this, and also a small, bigger one with this like this. So that's how we change this contact area parameters in our experiment.
Okay. Then, so you have like 7 experiments, right? So what do you think is the main parameters that affect the acid velocity?
Within the most significant.
Yes.
So it actually depends on how the parameter is changed. For example, if its height is actually reasonable and the height is really high, the velocity before the
Okay, so I ask in another way. So when you just set your height and you have your cushion, so there's like the pressure or the type of gas or like the Young's module or something else. What parameters affects the most?
So we didn't really compare those significant effects of different parameters, but in my perspective, if we exclude the velocity for the collision, I believe that pressure will be the
Or do normalization those parameters? Do you normalization those parameters so we can calculate what affects the most? Yes or no? Alright.
I don't really understand your question.
So through some math calculation, and you can know that there's some numbers like y affects like 0.56, and the pressure affects like 0.81 like this. So you can say like the pressure affects the most. Do you agree?
So as you can see in our experiment, in our theory, we propose a qualitative analysis for this problem. So this
Okay, so you
qualitative
have theory. So you can tell us which affects the most, right? You have theory.
In your explanation here, I believe you believe that each parameter has a kind of linear relationship between this x velocity, which is not true in our theory. So, and this quantitative analysis of this formula is actually not able to perceive in this qualitative analysis focus on our.
Oh, okay. And then another question: do you consider the energy loss through the wave transfer?
In our theory, we didn't really mainly focus on this energy. So I believe that this is a very good point that this energy loss should be considered.
So like the energy loss will cause the deviation, like your graph. There's like, and another is like there are deviations.
So you're saying that the ground.
So this is the theory. And this is the experiment.
Yeah.
Right. So it causes the.
So you're saying that our deviation between theory and experiment is caused by energy loss.
So what can you just guess or something through your experimental result? What caused the energy loss?
Energy loss.
Yes. What caused it?
So when we're discussing this collision, in general, there will be some energy loss depends on this material of the cushion.
Or how the wave transfer?
Wave is transferred in the cushion.
Time is up, so we'll be open to summarize the discussion.
Okay, so in our previous discussion, we talked about whether the recorder considered the rebound of the ball, and like is there any energy transfer difference when the balls are rebound. And we discussed about the wave that transfers energy, like the standing wave or something. And we discussed about the different launching angle reason and the different like contact areas. And moreover, we discussed about what exact parameters that affects the exit velocity the most. But I don't think reporter can give a very clear answer. And the boundary limit that causes the ball to be catapulted away is also. And thanks.
Reviewer, you will ask questions.
So the first question I want to ask the reporter. So discussion, you wanted to talk about how the wave process to catapult the ball, right? So can you please explain more clearly how the wave works on the catapultation?
So when the ball collides with the cushion, it creates two different directions of waves propagate through the left and the right ends of the cushion. And once because we put the ball usually at the edge of one side, so this reflection of the ball will collide with the other side and creates a standing wave that we mentioned in our theory. And this standing wave can catapult it through this change of amplitude.
Got it. So do you think that the difference of the wave air pressure would differentiate the results?
That included in our experiment that we changed the pressure of the air inside the cushion and it caused the change of amplitude, therefore an x velocity.
So what does it mean?
Okay, let's repeat that.
So do you think the air pressure difference would affect the phenomenon?
Definitely.
Yeah, right. So can you please turn? So do you have the data of wavelength or like frequency? Do you measure it? Do you know the wavelength or data of wavelength and frequency?
We didn't specifically measure the wavelength frequency.
Then how do you calculate the theory?
Calculate the theory based on the boundary condition given by those conditions of the ball and the catapult and crashing boost.
Then, but in your formula, you included a lot of like wavelength or like different conditions. Do you have all those data?
So you're saying if we have all of the data, we can do predict the x velocity instead. But our report focusing on using the qualitative analysis to explain the whole phenomenon. So we didn't really have every single variable sense in the formula.
Then how do you calculate it here?
We calculate the theory by using different results that we came from.
But you say that wavelength and frequency will alter, right?
Sorry?
Right. Okay. So.
I think it's necessary for the reporter to measure the frequency and the wavelength of the wavelength transfer.
Okay. So how do you fill the gas? So you change a different gas, right? How do you fill the gas? So is it pure, or maybe have it add on some Abi air?
Pure.
It's pure. Right. So what is that one?
I think it has to be pure, and I believe that reporter used pure gas.
See.
Right, we will have 2 minutes for the presentation.
reviewer from Team Discover, and today I'm gonna review problem number 16, question pattern. So this is a problem statement. So you need to place an element on large A question and investigate how the absolute velocity depends. So this is a theory they use. So they use Young's modulus effect and wave equation and amplitude analysis to explain the theory, and they use different mass of falling ball, different gases in the cushion, different size of the cushion, texture of the cushion, and different gas pressure to do the experiment and then set up the used fiber, pumper, and zipper. So, and the results are the exit velocity is related to Young's modulus and of the cushion, contact area, mass of the ball, pressure, volume, and size of the cushion, and size of gas. So I think they should have reported, and they tried a lot of parameters, and they understand the task well, but I think they lack a clear explanation for the use of wave equation, which is, they need to improve that, and I think they lack a consideration of energy transfer, and didn't clarify the relationship of pressure and the volume of the cushion, and they only use this wave to explain it, but I think that the pressure and the volume is very important in this phenomenon as well, and they didn't indicate how to measure the contact area. And they didn't specify the data of Young's modulus of the cushion in the setup. So maybe they need to provide the data so that we can more understand it. So, and they didn't explain how to measure the pressure and volume of the cushion. And they didn't explain how to fill the cushion with H2, N2, and CO2. And they only say that it's pure. So, and this is some of your opponents. So we asked about the explanation of the formula, and he asked about the physics process and phenomenon, and the energy transfer and pressure difference. So the experiment asked about the method of the measure and the consideration of the cushion stretch and how to measure the elasticity of the cushion and suggestion to consider air resistance. So the trend, I think they asked about some physics process and point out some problems on the setup in the experiment. And the suggestion is that they didn't have a solid structure for the question. They keep on asking like one and one. So I think, and this is a discussion. So the opponent asked, what do you think is the most important parameters? And the reporter said that they didn't focus on it. And I think that the filling rate of the cushion, which is how much air in it, might be the main factor in the phenomenon, but the reporter didn't consider it. So, and the opponent actually did consider energy losses. The reporter said that this is not the main consideration. And we think that how the energy transfer is a very crucial point to be discussed. And I asked about, do you have the specific data of the wavelength and frequency? And the reporter said that they didn't have the data. And the opponent said that they think it's important to know the data. And I think that it's important to use the data because they mentioned that the wavelength and frequency would alter and affect the result. But they didn't have the exact data to calculate the theory line. But somehow they got the theory line. So I think this really good. And so, and I asked about the reporter consider on the edge and the drop would be. I asked about how to feel how pure is a gas, but they didn't answer how to. But their answer is that it's pure, but they didn't know. But they didn't answer about how to fill in the gas. So I think it's also not. It's also important to know how.
Right. And for the reporter, to give the concluding remarks.
So, now I'm going to have my concluding remarks. First of all, the opponent focused on the angle of the falling ball, and we focus on the perpendicular angle of the ball acting in an experiment. And also, the rebound of the first ball does not constitute a significant part in our experiment and theory. And the significance of the 7 parameters can fluctuate based on the setup of the experiment. And focus based on our quantitative analysis, we did actually find out that those parameters fluctuate with the setup. So we can really analyze the most significance because it's based on the different intensity of those parameters. So, and we use the variables to calculate the wave function. But the wavelength and the frequency is the conclusion of this equation and is irrelevant to the calculation of the wave function. So we did measure the amplitude in order to calculate this theoretical results that's used in our calculation. And also, the reviewer talked about crushing the pure gas, but I think it's pretty clear that we just pump those pure gas exactly into the cushion. I don't find there's any problem about pure gas thing. And the reporter and opponent also mentioned this effect of pressure on this phenomenon, but as you can see in our experiment, we did mention those pressure difference and its cost to the x velocity. So we did put the pressure and volume into consideration. And we thanks the suggestion from both the opponents and the reviewers. Thank you.
Thank you. So time for the jury to ask questions, please.
Can you show your formula? The X velocity formula. The one you figure experimental data. Maybe any one of them. Okay.
Sorry?
The formula you figure experimental data. Or show the experimental data and then with the formula. I think you have one of the figure there. Okay. Any data will be fine.
Sure, correct.
All right. So in this, how do you get the theoretical point?
So we measure this amplitude of the ball through the video analysis.
Is there any fitting parameter here?
Fitting parameters.
Omega, where is omega?
We measure it through analyzing the video, using the high-speed camera to capture the frequency.
So that means you measure frequency, but you say you didn't measure the frequency.
I think maybe I didn't express my.
Okay, so that's confusing. Otherwise, how do you see the?
That's
okay.
problem.
All right. So you measure all the parameter in your formula.
Yes, but can you go to the initial first page about the velocity during verification?
Just answer me yes or no.
Yes.
Okay. All right.
May I ask a very simple question? They use wave equation, and also they mentioned about standing wave. I'd like to start from the reviewer and the opponent, then to the reporter. Do you agree with their? Do you agree to use wave equation to describe this phenomena?
No, we don't agree.
Why?
So, can I draw this quote?
Sure.
Okay.
Just keep it very simple.
All right. So,
Answers.
so when the ball is, when the object is put on the catapult and put on the cushion, and the ball is dropped onto the cushion, and so I think it's the pressure difference. So the volume will decrease and the pressure will go up, and also so that the object will be catapulted out.
Okay. How do you think? They use wave equation is anyway to describe the formula.
I didn't think so because since the air inside the cushion will make force to the cushion, then the wave on the cushion will just get break.
So you think it's wave?
I don't think they can use just like this wave function to describe it.
How do you use wave function? How do you state your point?
So I think the reviewer used the parameters such as pressure and volume is fairly reasonable. But in our equation, although we didn't directly, it's related to those pressure and volume, it didn't include in our theory. And
What's the assumption for you to use this equation?
I'm sorry?
Assumption? What's your assumption?
Assumption.
assumption to use the wave equation. Why is it use wave equation?
Because as you can see in our experimental video, we observed that there's a certain wave motion of the cushion when the ball actually collides with the cushion. So that's the reason why we use wave equation to explain this phenomenon.
So can I add one more thing? So the motion would be more like a seesaw, and we use that to assume.
Okay, thank you. So time for the jury to make the final decision for the grade. Okay, for the reporter's grade, there are 7, 6, 6, 5, and 7. Now, for the opponents, the grades are 6, 6, 7, 6, and 6. For the reviewer, the grades are 5, 7, 7, 7, and 7. So if there's no objection, we'll have 2 minutes break.